Well, we're making progress. We know how to represent molecules. We know how electrons, how important they are for bonding. We know how to represent the structure of molecules. But we have one other thing that we have to look at very carefully, and that's the periodic table and the atomic mass in that periodic table. Because it turns out when we're coupling the microscopic world with the macroscopic world, we need to know what the mass of each one of those atoms represents in the periodic table, because we're going to be taking a large number of those atoms and calculating what that means for a molecule or a compound. So that means that we have to develop the relative atomic mass of each of those elements in the periodic table. And the center of our discussion is going to be the carbon-12 isotope of carbon. Carbon-12 isotope of carbon has 6 protons, 6 neutrons, and it has 6 electrons. And by international agreement, this carbon-12 is taken as the reference isotope. That's an interesting term because we saw when we were analyzing the different elements that when we proceed through the periodic table, the number of neutrons and the number of protons is not necessarily equal one another in the nucleus. And so this becomes increasingly important as we get to heavier and heavier atoms. But this international agreement of carbon-12 taken as the reference isotope means that we've defined a mass of 12.000 atomic mass units for carbon-12, or AMU. So let's focus in on carbon right here. And we notice that the mass represented in that periodic table is not 12.000, but 12.01. So we have to find out and determine why that difference occurs, because it's very important in understanding the contribution of mass from each one of the elements of the periodic table to the mass of a compound. So the key point to note is that the atomic mass listed in the periodic tables are the weighted averages of the isotopic mix that comprises that particular element in the periodic table. Carbon, for instance, is an isotopic mix. And we can tell that immediately because rather than 12.000, its representation is 12.01 in the periodic table. And this comes back to the natural abundance on Earth. And in the case of this periodic table, each of these elements is represented as the natural abundance on Earth. And in the case of carbon, carbon is 98.9% carbon-12, and it's 1.1% carbon-13. And when we combine these as a weighted average, this turns out to be 12.01 atomic mass units. And lo and behold, that's exactly what appears in the periodic table. And this fundamental principle is true for every single element in the periodic table. And you can imagine how much work it took to determine exactly what the combination of these different isotopes were in terms of their natural abundance. So let's continue then and explore this in a little more detail. The masses of all the other atoms are then measured relative to carbon-12. So carbon-12 is the international basis. So the relative mass of hydrogen, for example, is 1.00794. You can see that there is a slight contribution from deuterium and tritium in that statement of hydrogen as an element. In the case of oxygen, that number is 15.9994. Oxygen is approximately 16/12 as massive as carbon-12, and hydrogen is about 1/12 of the mass of carbon-12. But now let's take water for an example. If we combine 2 of these hydrogen atoms from the periodic table with 1 oxygen atom, we're going to add up the actual atomic mass of naturally occurring hydrogen, and we have 2 of those, so we're going to 2 times that, plus the oxygen contribution, 15.9994, and that gives us 18.0153. So we can determine exactly then the mass of naturally occurring water by constructing it from its elements and taking the contribution from each of those elements in the periodic table that represents the proper naturally occurring abundance, that is the ratio of the isotopes, and calculate the molecular weight of any molecule. And in this case, H2O is fairly simple, but the principle is the same no matter what molecule we're looking at. Now, we've looked at cases in which the stated mass of each one of these elements is actually very close to the combination of the sum of protons and neutrons. So carbon was 12.01, but there are cases that differ significantly, and one of the important cases is chlorine. Chlorine 35 has a mass of 34.9689 atomic mass units, but the other isotope, chlorine 37, has a mass of 36.9659. But here's the interesting thing about chlorine. The chlorine 35 isotope is 75.77% of the naturally occurring abundance, and chlorine 37 is a huge fraction, 24.23% of that naturally occurring abundance. And so the average relative mass works out to be 35.45. And so when we look at chlorine in the periodic table, we see there's the very large contribution from that heavier chlorine 37 isotope in the determination of the atomic mass units corresponding to the natural abundance of chlorine on Earth.